There we go. All right, so I tried to make it to where I can have less of the calculator taking up my screen and having more of my notes there. So as we look at transforming data, we learned way back in Chapter 2 that we can transform the data. We don't have to add the amount necessarily to every single data value and then recalculate. We know that if we know what the original mean was, I can add, subtract, multiply, and divide numbers to the mean, whatever it was, to get the new mean. And that's as long as we're adding, subtracting, multiplying, dividing the same amount to every single data value, we're allowed to do that. And so that's what we're going to be doing today as we look at our random variable and our distributions here. We're going to be doing some transformations where they change the setting as we do stuff. So that's why we're putting this stuff in there. We can do the transformations. When we add or subtract a constant to each observation, we know that it adds to the A value or whatever it is, or subtracts it to each individual value's mean. It does not change the spread or change the shape. When we multiply or divide every observation by a certain constant, yes, it changes the value, the individual values in the mean. It actually multiplies or divides the spread by technically the absolute value of what you're multiplying by. And then it does not change the shape. So again, shape stays consistent no matter what operations you're doing. The spread, the variance, is the one that changes through multiplication and division only. And then all four operations change your individual measures of values like quartiles and those things in the mean as well. So here's our first example. We're trying to say, hey, do these rules apply to random variables like this new topic we're in right now? Pete's Jeeps Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. We're going to let X, define X as the number of passengers on a randomly selected day. All right, the probability that we have based on the data, the probability that there's 2 passengers is 15%, 25% for 3, and 35% for 4 passengers. 5 passengers are 20%, and 6, 5%. They asked us to find the mean, so we're going to quickly go in here and do stat. Go over to calculate, do a 1var stat. Remember, we learned yesterday that we can actually do the X value, our distribution X, in the L1, and then we put the probabilities in the frequency list. And then we get to go down and hit calculate. And then we know what our mean is. It's the X bar. So our mean is 3.75. Our standard deviation is going to be, again, lowercase sigma x. So that'd be 1.0897. We don't need all the digits, but as we get used to doing 4, we do 4. So there's my standard deviation, and there's my mean for just the original thing. And then we're going to practice transforming it as we go through and see what happens. Does the mean change? Does the standard deviation change? So we do 1var stat, and the L1 is column is the X list. L2 goes for the frequency list. All the way up until this chapter, we've left that blank. Now we get to use the frequency list to help us calculate the standard deviations in this setting. It's saving us from having to multiply down each value 2 times 1.5, 3 times 2.5, multiplying down, then adding up all those answers. That's what it's saving us. Okay, did anybody get what I got? Or did I have happy fingers? Anybody get the same mean and same standard deviation that I got?
Yeah.
You did? Okay.
Oh, yeah, that's the same thing I did.
All right. So in the transparent, notice here's our shape. There's our shape. Again, not a lot of data. We can say it's approximately normal. There is a drop off on the right-hand side pretty quick with 6 passengers. So now it says Pete charges $150 per passenger. We're going to let our random variable C describe the amount Pete collects on a randomly selected day. Again, C being what he collects. What's the mean? So we're going to go back into our table, And again, this is where we get to do things and make it a little bit quicker. Sorry, I want to go in table. Sorry. I'm going to go up to column header 3, and I'm going to tell it to take column 1, and I want to add 100. It charges 150, so it's actually times 150. So actually times 150 because I get 150 per passenger, and then I'm going to hit enter, and it automatically multiplies through for me all the way down. All right, we're going to copy that down a little bit later, that into a table. Now they ask us to figure out, well, what is the mean of this situation? So with that in mind, let's do a 1var stat. Go over to calculate, hit enter. I'm going to change list. My list is actually L3. So second 3. My probabilities are still in L2, so leave it in the frequency list. And then I hit calculate. And now I see that my mean, so mu sub c, because we're doing for collections, is 562.5. And my standard deviation is 163.485, or sorry, 457, sorry. 57. Ah, man, I really got those mixed up, didn't I? 587. There we go. Now, there's the standard deviation is what it came out to. Remember, we multiplied everything by 150. Now, to see if it worked, like, can we transform this through multiplication? The old mean, the original mean, was 3.75. When I multiply that by 150, just flat out multiply it. Just quit the screen. 3.75 times 150. Hey, I got that 562.5. Same thing with the standard deviation. If I do 1.0897 times 150, I get 163.45. Now, since we didn't use, since we calculated all the extra decimal places in the second example of doing it, we're going to be a little bit off in what we're doing, but we're pretty close. They both round to a 0.46 is what they both round to. So this is letting us know that, yes, we can do these transformations in our new setting of these random variables, of these discrete random variables that we're working with. So general rules for multiplying and dividing a constant for a random variables. We basically, it multiplies or divides the location and the center by whatever b is. We multiply or divide the spread, the standard deviation, by the absolute value of b. Now, why is it the absolute value of b? Well, if we think back to fundamentally how standard deviation or variance is created, it's each data value subtracted by the mean and then squared. And so after a subtraction problem, you could have a positive answer or a negative answer. But once I square it, it becomes what? Positive. So if they just, so with that in mind, that's why we're saying, hey, if I know what I'm multiplying by, doesn't matter if it's a negative 200 or it's a positive 200, I'm multiplying by 200. I take the absolute value of what I'm multiplying by, is what I do when I want to do the quick way of finding what the new standard deviation is. And then it does not change the shape. Here is the shape. They did it for us, the histogram, and if we compare it to the first one, it looks pretty much exactly the same. Still has that same feel. So a little note there, multiplying a random variable by a constant b multiplies the variance by b squared. So if we're multiplying by, in this case, 150, the standard deviation, yes, it got multiplied by 150, but the variance technically is the 150 squared. So 225, let's see, 22500, so 22,500. That's what 150 squared is. So keep that in mind. And again, the reason I put that little note there is, hey, sometimes they give us those things. And also because we work with variances a lot more later in this lesson. So here's one where we get to start going with this El Dorado Community College. I don't know if we come back to Peach Jeep's tours. We may come back to that. But we're going to be working with these El Dorado things here, the community college, for a little while. So we're going to go in there. Let's clear out our tables. I'm going to do a second plus 712 real quick and clear everything out. And then I'm ready to get into this El Dorado Community College. The EDCC considers a student to be a full-time student if he or she is taking between 12 and 18 units. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester follows the following distribution. Great, let's get those into our table so we can manipulate it. So we're going to go L1, we're going to do the number of units of classes they're taking, and L2 is probability, so let's take our time and get those in there. And usually 18 is the max load most universities will let you take. Very rarely will they let you take 7 classes and get to 21 hours. All right, I got my stuff in there. It asks us, what is the mean and standard deviation for the distribution? They say at El Dorado Community College, the tuition for a full-time student is $50 per unit. That is if T is equal to the tuition charge for a randomly selected full-time student. So T is equal to 50 times X. So let's go in there and I'm going to go up to column L3. And I'm going to say, all right, take L1, so second column 1, and multiply it by 50. And that's going to automatically convert from my table. So here's where we got a table down below in our notes here where we get to fill in 600, 650, 700, 750. And they could do this on a free response of the AP test. They could do something similar to this, a small little table here, ask you to show the transformation. So the tuition charge, of course, changes here from their units to now. It's based off of $50 per unit. The probability still stays the same. So we can copy down the probabilities. That's not going to change. The probability will not change as we transform the X value as we do transformations on it. And then so real quickly we get to bounce back and forth between Pete's and El Dorado. So we're going to do a one var stat here. So stat, one var stat. Again, I want to use column 3, so second column 3, go down to my frequency list, and we're going to do second L1, and hit enter. And I'm going to go back and get the other one here. So what is for the transform distribution, what is the mean of this? Mu sub t is equal to 732.50, and the standard deviation sub t is equal to 102.804426. Now, what we don't have is what the original mean number of units was and the standard deviation. So I'm going to quickly get that up on the screen for you all. If you want to do it, you can. You what?
I did that calculation earlier.
Oh, did you?
Yeah.
So you got the
The original one.
was it 1465?
Yep.
And then what was the standard deviation?
2.0561.
0561.
And I did round.
And you did round. Okay. Thank you, dear. So as we look at the original, did both of them get multiplied by 50? Again, we can quickly go through and do the math if we want to. Is 14.65 times 50, is that number that's there? Hey, it sure is. And I bet you anything if we do 50 times 2.0561, we'll get pretty close to that number right there. Okay? So, yes, it still holds in that case. So going back, we get to do Pete's stuff for a little bit. Yeah, see, we get to bounce around here. Pete's and then El Dorado. I'll get here. Okay, I guess we already. All right, so we have that one there. I'm going to write those down here real quickly, our answers that we just had there. So 735 mu sub t is equal to 732.5. That way we don't have to retype that in. We got that there for something later. And then 102.804, 102.804426. All right. I went ahead and just dropped it down. This is probably me when I was typing all this stuff up. I didn't pay attention, and I should have cut that out and then had that just down below and shifted. So now as they ask us, I'm gonna to look at. Consider the cost of Pete's stuff, reflects the random variable. Again, we already talked about what Pete's collection would be. We said the mean was it 562.5? And the 163.4587. So again, we can go back in, put Pete's stuff in there. We'll find out that, hey, yes, it's still applied with the multiplication aspect. Now what they asked us to do is if Pete's cost is $100 per trip to buy permits, gas, and a ferry pass. The random variable V represents the profit. Okay? When we find profit, what process do we do for finding profit? Is it revenue minus cost? Is typically what profit is, right? You know, so profit is typically defined as your revenue minus cost. All right, so we're going to get in there. We know what they went ahead and what they did was they gave us the table, and they went ahead and they said, okay, what's 300 revenue minus 100? What is 450 minus 100? So they went ahead and subtracted 100 from that previous table we had up here of the collected. And so to save us some time here. So now they're asking us, hey, what's the mean and what's the mean and standard deviation of this one? Now, how many of you already cleared out El Dorado? Out of curiosity, you all cleared out El Dorado? Okay. So with that in mind, I'm going to cheat off of you guys. What is the mean of this situation for profit? Did anybody do a one-bar stat yet? Put it in there. Just like, you know. All right, I believe it's 462.50. I believe when you go in there and you put those numbers in for L1 and the other ones for L2, you get 462.50. The standard deviation is 163.46. Now, did the profit, we subtracted 100 from each of the revenue things. Did our overall mean decrease by 100?
Yeah. Mm-hmm.
Sure did. What about did our standard deviation? Did it change? No, it didn't. It stayed. I mean, this one's rounded to the nearest penny, so the one up above still is rounded to the nearest penny. So standard deviation did not change. So again, since we were subtracting $100 from each of the revenue trips, subtraction affects the mean, but subtraction doesn't affect the standard deviation. As we look at our picture here, they asked us to compare the shapes between the transform by subtracting the $100 and compared to what we had prior. Did the shapes change? No, the shapes are still the same. The shape's still the same. our mean, the mean for profit was actually equal to the mean of our, basically our mean of our revenue. Do we have revenue defined with a subvariable? Collected. They use collected for the revenue. So mean of, there we go, Mr. Stevens. Mean of collected minus 100. So that's what we basically did. We could take the old one and do that. The standard deviation of the profit is technically equal to the standard deviation of the collected. The transformation did not affect that part. I used the word collected instead of doing like a C because the cost was $100. We subtract $100 cost for his stuff. So I wanted to spell out collected so we didn't misinterpret what the C was. So adding the same number or subtracting to each value in a random variable adds that number to the location in the center. It does not change the spread, and it does not change the shape. And so now, again, we have some things that we can check mathematically, but again, as we go through, they asked us to go back to that El Dorado situation. We know the tuition charge is $50 per unit. We have our table. We have the mean and the standard deviation we calculated earlier. They said in addition to tuition charges, each full-time student at El Dorado Community College is assessed a $100 per semester fee. If C is equal to the overall cost for a randomly selected full-time student, then C is equal to 100 plus whatever the tuition charge is. They asked us to figure out what is the mean and standard deviation of that. Well, first, let's grab a little table here. We got a little table below we can fill in. So if the tuition charge is $600, then that means, and I get a $100 fee, that's now $700 is what that student is charged. Then it would be $750, $800, $850, $900, $950, and $1,000. Boy, it would be great to have those as what the tuition charges are for a semester nowadays. I hate to say it. That's what the tuition charges back in the 80s and early 90s when I went to school was. But it wasn't community college. That was major university. I still remember writing my tuition check to the bursar's office, and it was like $750 and stuff. So, hi, probabilities do not change. So 0.25, 0.10, 0.05, 0.30, 0.10, 0.05, and 0.15. In thinking, again, we did an addition. So in thinking, my mu C should be whatever mu T was plus 100. So if it was the mean of the tuition was 732.5, then the mean of the overall cost should technically be 732.5 plus 100, which should be 832.5. Again, my standard deviation of the final cost, since we don't add, it should be equal to the original. Should be what the tuition charge was. So it should still be 102.80 or 0.80 cents, let's say. Now, what I can do is I know you guys deleted stuff. I think I still have. You put it back in? Okay. So if I go up here to column L4, I can tell it to take column L3, add 100 to it, and then now do a 1 var stat and use L4 as my X variable, my list, leave my percentages in L2, and then there I confirm. I have 130 or 832 is what my mean is, and then that 102.80 cents is what my standard deviation is. So some general rules for linear transformations on random variables, kind of putting it all together. Effects on a linear transformation on the mean and standard deviation. If y is equal to a plus bx, so we have a linear transformation of a random variable x, then the probability distribution of y has the same shape as the probability of x, so that shape never changes. The mean of y is equal to basically that formula, a plus bx, because again, we get to add and we get to multiply when we're trying to figure out the mean. When we're trying to figure out the standard deviation of y, then it is the absolute value of what am I multiplying by times the standard deviation of the original standard deviation. So it's the what am I multiplying by times the standard deviation of the x values. The variance is b squared times whatever the variance of x is, of the x variable. Remember, what's the relationship between variance and standard deviation? Variance is standard deviation squared. Okay, so you can think of your formula for if you need to find the new variance. You can either do this. If you don't have the variance of x, but you have the standard deviation, you can always say b squared times standard deviation of x quantity squared. And you'd want to use as many decimals as you do that. You don't want to round that standard deviation. Take them out as many as you can, and then square it, multiply it by the b squared, and that would tell you what the variance of y is. So you can do either one. It just depends on what kind of data you have. That's what it depends on. So here's an example where you get to practice just straight doing the transformation, not even given a table. They say one brand of bathtub comes with a dial to set water temperatures. When the baby safe setting is selected and the tub is filled, the temperature X of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. They say define the random variable y to be the water temperature in degrees Fahrenheit. Okay, when it's set on the baby safe setting. What is the mean and standard deviation? So we want to know what is the mean of y and what is the standard deviation of y, our new random variable. Well, mean, we know that we can take, when I convert this over to Fahrenheit, I can actually use that whole formula since it's a linear formula. I can take 9/5 times my degrees Celsius, which was 34, that was the mean, plus 32. And so we would do 9 times 34, divide it by 5, then add 32 to it. You get an answer of approximately 93.2 degrees Fahrenheit. For the standard deviation, we're not allowed to do any adding or subtracting, so all I'm allowed to do is take 9/5 and multiply it by the standard deviation of 2 degrees. And that one would give me approximately 3.6 degrees Fahrenheit is what the new standard deviation in Fahrenheit. Again, we have everything down here in America in Fahrenheit and so forth, and most of the rest of the world uses Celsius is what they end up doing. So this is how we can convert it over. According to Baby R's Us, the temperature of the baby's bathwater should be between 90 and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe mode meets their recommendation. Show your work. So with this in mind, I'm going to go back and go up to this problem up here and highlight. They tell us that it follows a normal distribution. So as you look at examples and problems, as you read it for the first time, maybe highlight normal distribution, because that means later on now, as we try to calculate a probability, I can use that normal CDF feature to calculate the probability. So now, with that said, I can figure out, okay, what's the normal CDF with a lower bound being the temperature of 90 degrees, the upper bound being a temperature of 100 degrees. My mean, I got to use the Fahrenheit mean. The mean for Fahrenheit, mu sub y, was 93.2. And the standard deviation for Fahrenheit is equal to 3.6. I do not want to use the Celsius stuff when I do this, because we've converted it over. They're asking us between 90 degrees Fahrenheit and 100 degrees Fahrenheit. So now we just go second vars, go ahead to normal CDF, 90, 100, 93.2. Whoop, that's a 9.93.2, and then 3.6. And then I hit enter a couple times. And this tells me 0.7835. So so when we look at it, find the probability of the water on a randomly selected day. On a randomly selected day, the water will be about 78% of the time will be between 90 and 100 degrees is what that's telling us. Next example says in a large introductory stats class, the distribution of X, which is our raw scores on a test, was approximately normally distributed. All right, great. Mean of 17.2, so mu X equals 17.2. I'm going to go ahead and write that down. Standard deviation of 3.8, so standard deviation sub X is equal to 3.8. Again, I went ahead and since they gave us a variable that they defined for our distribution as X, I went ahead and used that as my subscript. The professor decides to scale the scores by multiplying the raw score by 4 and then adding 10. We're going to let y, the variable y, be the scaled score after the randomly selected student from each thing. So what's the new mean? So they're asking us to figure out what is the new mean of the scaled scores. And what's the standard deviation for the new scaled scores? So what's mu y and mu sub x? All right, well, mu sub y would be equal to mu sub x times 4, because they said we multiply by 4, and then add 10 to it. So that means I can go 4 times 17.2 and then add 10. That should give me 78.8 is what that should give me. And again, on a free response, that's the work we're showing. Show that our new random variable, the mean of it is equal to the other mean times the 4 plus the 10. Real quickly show the math. It's not that hard. It's pretty quick to do. For the standard deviation, all I'm allowed to do is multiply the original standard deviation by 4. So it's 4 times 3.8, which is equal to 15.2. They didn't ask us to define. They didn't ask us to interpret, so we're good. All we had to do was find it, not define or interpret stuff. Okay. What is the probability that a randomly selected student has a scaled score at least of 90? So what's the probability that y is greater than or equal to 90? Well, that's going to be equal to, we're going to do a normal CDF. Lower bound is 90. Upper bound. Again, I'm just going to put, even though we can't get above 100%, I'm going to put 10,000. Our mean y is equal to 78.8, and standard deviation of y is equal to 15.2. And then now I'm ready for the calculator. Second vars, normal CDF. We got the 90 in there already from the previous one. I'm going to go ahead and put 1,000, 10,000, whatever it is. Put in 78.8 and 15.2. Hit enter a couple times, and I find that it's 0.230609. So there is a 23.06% chance of selecting a student, and they'll have a scaled score of greater than 90, greater than or equal to 90. Any questions so far? It's a long lesson. We're just partway through. We're doing a lot of transformations as we do things. Okay. Scrolling up. We're going back to Pete. But there's also an Aaron in the picture. So as we look at combining our random variables, adding and subtracting random variables, let's investigate the result of adding and subtracting random variables. Let X equal the number of passengers on a randomly selected trip. With Pete's Jeep's tours, Y would be the number of passengers on a randomly selected trip with Aaron's adventures. So we went ahead and gave you what the mean for, we had what Pete's Jeep tours mean and standard deviation was. Went ahead and gave you the mean and the standard deviation of what Aaron's stuff was. Now we have a sidebar question. What are the variances for each of those? So there's where we got to remember that the variance is equal to the standard deviation squared. So real quickly we can go in and say what is 1.090 quantity squared. Ooh, we forgot the 1. 1.09 quantity squared. And that gives me 1.1881. And then on the next one, we would go 0.0943 quantity squared. And that would give me 0.00889. So now we got some questions. We know we can do transformations inside of a one random variable. The question now is, am I allowed to add these two random variables together, these situations together? And will the mean be, like in this case, and we get to test it later as a theory, but in theory, as we do it in practice, can I just take the two means and add them together? Can I take the two standard deviations and add them together? Can I take the two variances and add them together? As opposed to having to do what we're going to see here in a minute. And so that's what we're going to explore here is, we're thinking based on what transformations we're talking about, but in general, can I add just the two things together? Can I do the mean of X plus the mean of Y? So that would be okay. Can I do 3.75 plus 3.10? And that would give me 6.85. Now we're going to test it here in a minute doing the math and doing the calculations. What do you think the standard deviation of X plus Y is? Well, in theory, I think we could add them together. 1.090 plus 0.943 gives us 2.033. Why not? If I can add those two, let's go ahead and let's say, well, I should be able to add it all. So 1.1881 plus 0.00889. That gives us like 2. Hey, was I off on my happy fingers on that? Oh, I did. You didn't tell me that. Or you guys been like waiting to tell me. Or were too embarrassed to tell me. There's one less zero there. There's one less zero there. Because that's really going to screw up the next part. All right, so there's one less zero there. 0.0889. That gives us, there's a big difference there. 2.077. Okay. I didn't realize till I looked back up that I had the zero instead of 0.93.
There should only, or it should only be
0.889?
Yeah.
Okay, so 0.889. So I adjusted, that should be
Technically, you want to go out to the 4. There's
0.8892.
Yeah.
There we go. The reason, no, I was off because of my cheat sheet notes in my hand. I could see that I didn't have the same number that I was getting ready to make. So that's why I know it was off.
Absolutely.
So, Yeah, I know. Me neither. I was just flying. So let's check. So here we go. Basically, here's the table we're going to type in. We're going to type in, if I go through and add each of the different, 2 passenger, 3 passengers, 4 passengers, so forth, what I'm going to have to do is kind of create this big thing right here. And then this is the nice little, simplified little parts there. So let's go ahead and type those in to L1 and L2. You know what? Second plus 712. Get me out of there faster. There's too many columns to delete. So 4, 5, 6. Oops. Yeah, 4, 5, 6, 7, 8, 9, 10, 11. Okay, then go over here, and I say 0.045, 0.135, 0.235, 0.265, 0.19, 0.095, 0.03, 0.005. Now, the reason why we just aren't doing like 2 through 6 is because, let's say Pete only had, 2 passengers on a day, but as we paired up days with Aaron, it was maybe Aaron had 2, had 3, had 4, had 5, and so that's why we're not going like 2, 3, 4, 5, 6. There's a multiple combinations, and that's where we have in the middle there of all the different combinations of adding things together. So now I'm ready to do a 1var stat. And then I'm going to go in a frequency list. I'm going to do second L2. Go calculate. Here we go. We have a mean of 6.85. Standard deviation of 1.4413533531. Now, it doesn't give us our variance. Now, real quickly, as we look up, the mean matched. The standard deviation did not match from what we were thinking. Now, to find the variance, remember, here's some shortcuts. If I go and press VARS, go down to option number 5, statistics, then I can go down and grab option 4, lowercase sigma x, put it on my screen, and then tell it to square it. And that takes all those decimal places, so I don't have to do that. Again, it was VARS, option 5, find out which statistic you want to use, and then there we go. The variance 2.0775. Hey, that was pretty much what we had. So can we add the means to get the mean of the sum? Yes. Can we add the standard deviation to get the standard deviation of the sum? No. We can add variances. So, when we need the standard deviation, convert to variances, combine where I basically say we're going to add, and then take square root. And that's what we're going to get a practice of doing here in a minute. So, yes, we can go ahead. If we have 2 random variables, we can just add their means together. If they give us standard deviations, we're going to have to square them and make them variances, combine them, and then square root it. And we're going to be adding as we do that. So, I'll leave that little chicken scratch on there in case you need that statement there. I think the next part is filled in for you. The only way to determine the probability for any value t is if x and t are independent random variables. If knowing whether an event involving X alone has occurred tells us nothing about the occurrence of any event involving Y alone, and vice versa, then X and Y are independent variables. In our probability models assume independence when random variables describe outcomes that appear unrelated to each other. You should always ask whether the assumption of independence seems reasonable. In our investigation, it is reasonable to assume X and Y are independent since the siblings, Pete and Aaron, operate their tours in different parts of the country. That's why we could do it for this one. Okay? If they did it in the same area, hey, it may not be independent anymore. And that's what that's talking about there. All right, so the mean of the sum of random variables. Whew. There we go. Technically, you don't need, if you want to take like the white pen tool, you don't need that thing right there. So our expected value, remember capital E was typically our expected value. We learned that yesterday. Our expected value of t is equal to the mean of t, which technically is equal to mu of variable x plus the mean of variable y. So the expected value of t is actually the mean of t, which we know we can just add the two means together. So in general, the mean of the sum of several random variables is the sum of their means. So if we had 3 random variables, we could add all 3 of the random variable means together to get the mean of the total. Okay? If I have to do standard deviation, different story on how I have to go about that. And that's what we get to practice here in a bit. For any 2 independent random variables, x and y, t is equal to x plus y, then the variance of t would be equal to the variance of the random variable x plus the variance of the random variable y. Since variances is the standard deviation squared, we could say that the standard deviation of t squared is equal to the standard deviation squared of x plus the standard deviation squared of the y variable. And therefore, if we need to find the standard deviation of the random variable t, which is the combination of the two things, I just square root the sum of the squared standard deviations. So the variance of the sum of several independent variables is the sum of their variances. And then the standard deviation of the sum is the square root of the variances, of the sum of the variances. And that's what we got. That's what kind of a little side note. You know, the standard deviation is the square root of the sum of the variances. We're not allowed to add standard deviations together. That's what we need to keep in mind. We got to convert them to variances. Then we can add, then we can square root. Is it okay for me to scooch it up to about there? In case some of you are still writing. Really doesn't help me. There's nothing there to read. So I don't want to be going, I know I'm going quick. Back to El Dorado. Now, we're not going to have to really type in a lot of this stuff because we're learning about these transformation things, so we should be getting a good gist of it. So at the EDCC considers a student to be a full-time student if he or she has taken between 12 and 18 units of classes. The number of units X and that a randomly selected student at El Dorado Community College is taking in the fall semester has the following distribution. So they tell us that the mean is 14.65 credits. The variance, which usually we're not given that often, they gave it to us, is 4.23 units. And they give us the standard deviation of 2.06 units. So they went ahead, original problem, got us that information. Now we're going to look at doing some transformations without having to type them into the tables. That's what the purpose from here is let's not have to do the tables, do the little one-var style calculation to figure out, can we use some of these transformation rules. The EDC has a downtown campus specializing in just a few fields of study. Full-time students at the downtown campus only take 3 unit classes. Y is equal to the number of units taken in the fall semester by a randomly selected student at the downtown campus. Here's the probability distribution of Y. So they either take 12, 15, or 18 credit hours. Here's what we have, 30%, 40%, 30%. The mean, variance, and standard deviation for the downtown is listed over here to the right. They're asking us if we were to randomly select one full-time student from the main campus and one student from a full-time student from the downtown campus and add their number of units, the expected value of the sum would be what? So what is the expected value for the sum, the total? And we're going to say T is equal to the downtown plus the main campus. Downtown plus main. Well, we know we can just add the two means together. What's the mean of the downtown plus the mean of the main campus? Well, that would be just 15 units plus 14.65, which would give us 29.65 units. Again, we don't have to go in and combine all the things in combinations. We know we're allowed to add the two means together. Then they say, what's the standard deviation? Here's where we got to be careful. We're not allowed to add standard deviations, but we're allowed to add variances. So the standard deviation of the total would be the square root of each individual variance. The variance of the downtown plus the variance of the main campus. So the standard deviation of our amount here would be, again, they gave us variances, so we're going to use them. 5.40 plus 4.23. So that's the square root of 9.63. So second square root 9.63. And we get something like about approximately 3.1032. So there's our standard deviation for that situation, for the sum of randomly selected student from downtown and one from main campus. Anybody need that any longer? Are we okay? All right. So as I zoom in and scroll up, it says let our random variable B, let B be the amount spent on books in the fall semester for a randomly selected full-time student at the college. Suppose that the mean of the books is 153 and the standard deviation is 32. And they said, recall from earlier the cost, the overall cost for a person on main campus or a randomly selected full-time student at El Dorado was 832.50 and standard deviation 103. They asked us to find the mean and standard deviation of the cost of tuition, fees, and books, so C plus B. So the mean of C plus B is equal to the mean of C plus the mean of B. That's what we know. So we can say, all right, I can take The mean of my cost is 832.50 plus 153. And then that gives me 985.50. 985.50. What is the standard deviation of C plus B? Well, remember, I got to do the square root of the variances. Here's the challenge. In this situation, did they give us variances? No. They just gave us standard deviations. So here I got to make sure I take the standard deviation of the cost squared plus the standard deviation of the books squared. So I got to figure out, okay, what's the square root of 32 squared plus 103 squared? And then I get to add those, square root it. So second x squared, and then I'm going to do 32 squared on the inside plus 103 squared on the inside, and hit enter. And it tells me that the standard deviation is 107.8564. So about 107.86 cents. Again, we're not given variances that often. We're typically given mean and standard deviations, or even if we did this by hand, we have to calculate the variance by taking the standard deviation and squaring it. Then we get to add, and then we get to take the square root of it. So we just did the mean of a sum. Now we're going to talk about the mean of a difference of random variables, meaning we're subtracting the two situations. Is there any difference? Am I allowed to subtract the means? Am I allowed to subtract the standard deviations? Now, typically, what do we think? If we're allowed to add means, do you think we should be able to allow to add or subtract means? Sure. If I'm not allowed to add standard deviations, am I allowed to subtract standard deviations? No. So that means when I get to that part, we're going to have to do the variance thing again. But we got to be careful. So if you're working ahead of me, be careful. Okay? If, for any two independent random variables, x and y, if d, standing for difference, is equal to x minus y, then the variance of d is equal to the variance of x plus the variance of y. Since standard deviation is squared, variance of standard deviation is squared, we can say it's the standard deviation of x quantity squared plus the standard deviation of the y variable squared. And then therefore, when we go to find the standard deviation of the difference, we would just take the square root of each of those things. Even if we are subtracting our random variables. Do what?
Addition symbols.
Yes, they're addition symbols. Even though we are subtracting, we are still adding. Even though we are subtracting, we still add. It doesn't matter if you're doing a difference or a sum of the random variables. When you're doing the variance, you're adding the variances. Okay? Part of it, you can go back from the standpoint of if I did the big table by hand and typed in all that, like we did with they had with the Pete and Aaron tours, and we did it, we would notice that they didn't subtract stuff. When we did the calculations, it was actually always adding. And the reason is because of the squaring. When we square a part of each of those little formulas to get stuff, everything's positive. And so there is no subtraction. So that is a little note. So we're always, and this is, and I don't know if this is on that cheat sheet formula for the AP. But it's something that you need to remember, because that's where I typically find kids make mistakes. No. So that's something I would highlight. I would highlight, put a star. that you always, this thing here, you're always adding variances. You're always adding the variances. Even if it says it's a difference, you're still adding. The only time that you actually subtract is when it's the means. Okay? So we see that come up on multiple choice tests on the AP exam. We also see it pop up otherwise. So here's an example where we get to practice it. The mean of the main campus credits T, main campus credits T is 1465, variance is 423, standard deviation, blah, blah, blah. The mean of the downtown campus, we had that there. Suppose we randomly select one full-time student from each campuses, and what are the mean and standard deviations of the difference in tuition charge? So we want to find the mean of the difference, which technically is the mean of T minus U. So we can do the mean of T minus the mean of U. So that would be 14.65 minus 15, which is a negative 0.35. And it's okay that it's negative. When they talk about these things and we got to do a difference, you got to do it in the order that they tell you. Is there a difference? And they usually give this kind of little script there to let you know what order they are expecting you to subtract. So pay attention to that there. It's okay that this mean difference is negative. Now, for standard deviation, we know we got to convert. Well, we don't have to convert. They do give us standard deviations there. So we would say, okay, the standard deviation of T minus U would be just, or not standard deviation. Did they want variance or standard? What are these? Yeah, standard deviation. Okay. So with that in mind, I got to do the square root of, technically it's the variance of T plus the variance of U. Since they gave me variances, I can make this quicker and say, all right, it's 4.23 plus 5.40, square root of 9.63, which we already had, 3.103. This was a long lesson. All right. Combining normal distributions. I'm down to one side of the piece of paper only. So that's how much we have left. Okay, so we're almost done. Okay. I don't know, maybe not. Hold on a second. Okay, what's next? Combining normal distributions. Yeah. That's all we have left right there. Oh, yeah, sweet. All right. So if a random variable is normally distributed, we can use the mean and standard deviation to compute probabilities. An important fact about normal random variables is that the sum or difference of two independent normal random variables are normally distributed. So we got two examples we get to go through. We got Mr. Powell as our subject in the first one. Mr. Powell likes between 8.5 and 9 grams of sugar in his hot tea. You didn't know he was a hot tea drinker, did you? Suppose the amount of sugar in a randomly selected packet follows a normal distribution with a mean of 2.17 and a standard deviation of 0.08. If Mr. Powell selects 4 packets at random, what is the probability that his tea will taste right? All right, great. So we said it was approximately normally distributed, which means I need to use the normal CDF at some stage. The challenge is it's not just one packet. The mean and standard deviation they give us is for one packet, but he's grabbing 4. He needs 4 packets to get his thing to taste right. So what's the probability that it will? So with that in mind, we need to find the mean of the 4 packets. Again, we have learned that we can just add means together. So that means that I would have, I went way down there, sorry. Mean of 4 packets. Then that means I have 4 packets times 2.17. You can do 2.17 plus 2.17 plus 2.17 if you want. But that gives me 8.68 grams. Now, the standard deviation for the 4 packets. Well, that's going to have to be the square root of 0.08 is the standard deviation of 1 packet. I have to square it. Then I got to do that 4 times because, again, we got to convert to variances before we take this before we can find the square root of the standard deviation. We can't combine standard deviations together. So I got to go 0.08, for each packet squared. Now you could say 4 times 0.08 quantity squared if you wanted to shorten up the math. You could do that. That works out to save you some time. About 0.16 grams roughly is what that works out to be, just to save you a little bit of time. Now, what is the probability? So now we finally get to our normal CDF. Normal CDF. And we get to go lower bound is they said between 8.5. So a lower bound is 8.5. Upper bound is 9. My mean was the 8.68 we just found. And the standard deviation was 0.16. So as I go in here and do a normal CDF, normal distribution CDF, we're going from 8.5 to 9. 8.68 is my mean. 0.16. Hit enter a couple times. And we get 0.846955. So about 84.7%. There is an 84.7% chance Mr. Powell's hot tea will taste correct when randomly choosing 4 sugar packets. Okay. That's a pretty good probability. 85% chance that it's good when he just randomly picks the packets and so forth. I don't know how you wouldn't do it any other ways. I don't know how you would analyze sugar packets any different to know which one's going to be better or not, but are they all, do what?
Put them on scale, weigh each individual.
Yeah, exactly. You take what in there, take into account for the pour it out and on a scale and zero it out and and kind of go from there. So last one here, again, you can work ahead of me if you want. We're doing the same kind of thing. They're asking if on this one we're doing, is there a difference? So suppose male height, suppose the height of male speed daters follow a normal distribution. So that, again, lets me know I can do a normal CDF to figure out a probability. They have a mean, so mean for the males is 70. Standard deviation for the males is 3.5. And then for females, speed daters, again, it also follows a normal distribution. Great. With a mean, so the mean for females was 65. Standard deviation for females was equal to 3. What is the probability that a randomly selected male speed dater is taller than the randomly selected female speed dater? So probability that male is greater than female. So that would be males minus females is greater than 0. So we're subtracting the females from the males as we look at our operations. That allows us to know how we need to do our means. The whole reason I did that was so we can figure out our mean. We need to take the mean of the males minus the mean of the females. Mean of M minus F. So that would give us 70 minus 65 is 5. Standard deviation of males minus females would be the square root of the standard deviation of males squared plus the standard deviation of females squared. So that would be the square root of 3.5 squared plus 3 squared. So that would be the square root of 21.25, which is approximately 4.61. Just chopping that off. Now you can, in that normal CDF, if you want to be really precise and accurate, you can actually type in the square root symbol in that part right there. And then after that little, in the normal CDF feature, you can type in the square root of 21.25. And sometimes with some of the stuff we're doing a little bit later and we need greater accuracy, we're going to do that. We're going to take the square root and type that whole square root piece in there. So we're going to go second VARS, normal CDF. Our lower bound, what is the probability that a selected male is? So our lower bound is 0. So normal CDF. Why is it 0? And not just because Mr. Stevens said so. Do what? Yeah, exactly. So and then now what's the upper bound? We're going to go really big, huge number. And then we go the mean is equal to 5. Again, standard deviation, you can type in 4.61. I'm going to type in the square root of 21.25, and I'll show you the comparison between the two decimals. So, again, 0, really big number. And then we have 5. And then I'm gonna do second square root 21.25. Hit enter, hit enter, hit enter again. And that gives me 86.1%. Technically, it was 0.86096, but then we went ahead and rounded up. When I did this in my notes, and I used 4.61, and when I used that one, it gave me 0.861. It went ahead and almost did the rounding for me, is what it almost did. So by using that, it gets us a little bit more accurate, with especially some of the other stuff we're doing with confidence intervals and some of our other things. We want to be more accurate as we do it. So there's an 86% chance that a male speed dater is taller than a female speed dater. Boom.